So let me remind you briefly what was happening on the previous lecture. And so it was about entropy, and the picture, the mental kind of the ideology behind that was that there is a big physical system, like a crystal, which you want to observe. This, because infinite has infinite entropy, eventually, and today I shall do that, we have to define its entropy, which is entropy per unit size, so to speak, properly normalized, which will be finite. But what we have at the very beginning, this is a kind of abstraction. Experimentally, we observe our physical system through kind of some apparatus, some device, and we see something flashes, boom, 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 and nothing else. So the one thing which we have, we can count them. And secondly, what we can say that eventually will be used, we don't know, there is no meaning of that. Out of that, you define this entropy and give it some interpretation. But the only thing which are in your position, this blinking, which is systematic, and you can count how many happens per unit time, so time at your disposal. And secondly, you know, if you have this crystal and you can move it, the whole thing you can move, and you know it is the same. And that's sufficient to define entropy. And actually, everywhere in physics you don't have more. Everything else you construct. You have this boom, 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 and you know the certain situation postulated to be the same. They postulated to be the same, yeah. We don't know. Of course, there are other kind of postulates. You can say two things in a different part of the universe. What happened there is mathematically independent, but this, as we know, very careful. It's not quite true in quantum mechanics. Intuition breaks down. And now entropy, so this system are modeled, this finite system are modeled, but what is called finite probability space, may go one line up, which you defined before. So it is just finite set of atoms. And so there was some justification of kind of categorical language. So, but just remind me, because I'll be elaborating on this today. So we have there's finitely many atoms or finitely many drops of water. So they're called finite measure spaces or probability spaces. So they're finitely many. We call them atoms, but can think about drops of water, and total mass is 1, it's normalized to be 1. So there are numbers involved in that, which already kind of course, tricky, because numbers have no, real numbers have no physical reality, of course. As I said, what has reality is only this kind of, this events which you can count and you cannot differentiate, and notion of identity between certain observations, which means there is some symmetry in there, right? And so this is notation, which I keep, just to look at that. So it is a set with weights, and if you forget about the weights, I just say set, right? And so there are two different words, just sets and set with weights. And notationally, it's, I think the way I set up notation is rather efficient. Then there is a little point which looks completely trivial, that if you allow things with mass 0, just when you speak about infinite measure space, there are kind of huge sets of measure 0 which you throw away, and but here just atoms which don't participate in anything. However, we shall see, not today, maybe tomorrow, that next lecture, that in quantum probability these atoms, these 0 atoms, kind of essential. They kind of change mathematical framework, and so this is normalization, and this is my notation also. So I'm proud of my notation. I don't have to have subindices, you see. I don't have, this is usual, kind of, there is misdemeanor in mathematics. People use subindices because they introduce artificial sets which are not in the game, right? There is no i's here because they're not ordered atoms, they're just sets. And then there is this concept of reduction, this physical terminology, and in my view very, oh, why, what happened? It doesn't want to move now. It was moving all along, and now it refused to. What happened? We missed it. What happens to this system? Yeah. Doesn't help. Yeah?
You have to move the arrow.
You have to move the arrow.
Yeah, and then click.
Now maybe it will. Now you can do it by hand. Oh, okay. No, that's okay. Yeah. is even better. And so this is a key concept. There are probability spaces and reductions. And reduction, again, have very simple interpretation. 2 drops of water comes together, several comes together, and masses, of course, add. And these are arrows, and they look extremely extremely primitive. The number of arrows almost the same as, it's even smaller than but just for sets. However, we shall see it is quite convenient. This language of arrows is extremely convenient. And there is this operational product, which you just take all these pairs and with these weights. And here you see multiplicativity of numbers involved. So numbers are there, yeah, you see, but these numbers will be just frequencies of some events. They come, of course, from counting. They're not coming from measurement, you see, that's the point. You don't measure size. This kind of extremely complicated process. All you can do is count events, and you have kind of time comparison, which is, as you know, in relativity, the only thing you have is you have t. You have timer. You have way to measure time. You have clocks. You don't have any meter. Everything, and then I make some justification of why categorical notation, much concept more flexible, even if you don't speak about generalization, already better than this. And then there is this kind of motto or thesis: entropy is a number equal to the logarithm of the number of states. So first, entropy is a number. It's a real number, right? Which is very many things in physics are real numbers. And this is one of the things we shall challenge, right? Many things are not numbers, despite what we always like to say. And then what are properties of this entropy? And so I just enumerate them, and they make sense, whether this number, not numbers, but. So one is very simple, and this is kind of quite essential, that if we have 2 non-interacting systems, then entropy is additive. Of course, you could see multiplicative, taking log or not log, but we shall see log is not so stupid at some moment. And symbolically, see is 1 and 2 very far away, and entropy is that, and this is the picture. So what you think about and that's essential, that we have a big thing like a crystal, and you have measurement here and measurement very far away, and so entropy assigned to these results of measurements, infinite system per se, has no kind of intrinsic entropy, but you see how many blinking you have here per unit time, how many you have there. Somehow you measure entropy, whatever it is, and this must add up. Again, because if they're far away, they don't interact. But of course, it is a postulate. Yeah, it may interact, but you believe they don't. After all, this is the point of the distance. If they do interact, means they're not far away. This is how you define distance, after all. But next, this is kind of rather simple. And secondly, it's more subtle. It is this symbol means join, means 2 systems join together, but they may interact. Not necessarily, but may interact. So what is this join? When product is defined, this is not truly operation. Again, we have my picture. This symbolically how you write it down, and this how you imagine the picture. You have 2 systems next to each other, and so they're close and they may interact. And again, intuitively is that because they interact, so one state in one may prevent. So we have some little wheels, and the only certain position between them are acceptable. The number of states goes down. But what is this joint? Yes, it's not really operation. Yeah, it's just some position, relative relation between them. There may be the system joined of the 2, but it's not canonical operation. If you know this probability space and this probability space, you don't know, unless they're being used for measurement of the same system. Then joint always makes sense. They might have physical implementation in the same world, so to speak. If they're not, then it makes no sense. So you need this world where they're implemented. So, and this one possible definition, which is enough for applications, but this is which I haven't explained last time, very simple. This is if they don't interact, then this is definition. But in general, this symbol must depend on how they interact. And one possible definition of that. So it's not canonical operation. So it is a Q is a subset here. So set set of states of Q is subset of the product. It may be many different subsets, so it may be positioned in many different ways. But whichever of them it is, you call it joint, and then the projection must be reduction. There is some words in mathematics people use for this reduction, this marginal something very, I think, very strange words, which I call in probability theory, this is language, which is less, in my view, much less flexible and less categorical than the physical language, by the way. It's interestingly enough. Physicists use really almost categorical language, mathematicians use that. And so this is quite intuitively clear. Whatever entropy is, if it is intuitively the number of states, it must be this property, but the strong subadditivity is not. So this is what it says in one notations, and this is what it's more compact notations. So the key point is you estimate 1, 2, 3, sum of the two minus a term. And that's tricky, so there is minus there. So there is some kind of cancellation. And if you use these joints, it means the set is subset of the product, where the coordinate projection are reduction. So that's kind of rigorous definition of what I said. Right? Because this joint was somewhat vague, this is how we understand it. Okay, and that's the picture, because I couldn't make this, so this is the picture. 1, 2 is not in the picture. And this one of the corollaries doesn't quite fit. And then there is this property. If something is reduced, entropy goes down. And this looks completely kind of the simplest of all. And it must be always so, but it's not the quantum case. That's quite remarkable thing. Many think quantum theory remains, and this is not. And this is what's called, people speak about entanglement, some words which are impossible to understand. But essentially it amounts to that. That when you look at a single object in a quantum observation apparatus, you can see many of them. You can see more states than you see is there, so to speak. Because you cannot separate apparatus by which you observe from the object you observe, philosophically. Mathematically, it's certainly some linear algebra involved, which will come back. And then there is another property which is I got it almost an axiom, but again you have to have it, which is not completely apparent from this intuitive definition, but it should be smaller. And then you and the equality is when all atoms have equal weight. So that's it. So just again with entropy, whatever, there is no definition. I think you cannot give truly definition, but this is roughly what you expect, what may be there, and people just modify definition, find new definitions, playing with this property. And then the point is that the existence of such a function is quite remarkable. It's not, it looks kind of just number of states, you just say it correctly and then you finish. But the example I was bringing forth, for me it was kind of a revelation that there is the following inequality. So this is a classical isoperimetric inequality given subset in the Euclidean k-dimensional space, volume bounded by area, so to speak, of the boundary. It's volume. When I say volume on the right-hand side, it is dimension n-1, which I failed to write down here. Volume of the boundary means n-1, k-1 dimensional volume. And there is this inequality which is significantly more precise. It said that if you take such a subset, that its volume bounded by k-1 volumes of the projection of the coordinates hyperplanes. So there are k projections. Say in 3 space there are 3 projections of the plane. So there are the sets in the plane, and these bound the volume, and where the equality holds for solids and whatever obtained by measurable transformation preserving coordinates. And this is stronger, because when you project something, an area of the, say in 3 space, whatever you project on the plane, area of the projection is less than projection of the boundary, because only point on the boundary enter into the projection, right? Because any line which meets a set also must meet its boundary. It's simple topology, but amazingly enough, it's non-trivial. And if you ever thought about isoperimetric inequality, it's not trivial even in this weak form to prove, even when it's non-sharp. Actually, there are many simple proofs, but still none of them is trivial. Yeah? And as I said before, all Sobolev inequalities are kind of trivial corollaries. Trivial meaning modular linear, kind of stupid calculations follow from this isoperimetric inequality. And this is sharper. This implies so-called log inequality. And this all follows from strong subadditivity in the first non-trivial case, when it's three-dimensional space, and these notations we use this kind of a three-dimensional shape in 3, and then that's its projection to 3 planes, and that's the inequality. I wrote explicitly. It's product. You see, it's another point. It's not sum. This area of the boundary related to the sum of this projection, but not to their product. Product a priori is smaller, and therefore it's sharper. Why I say it log Sobolev. It's sharper than usual inequality. And the proof goes is derived from, first we approximate it, and we can divide everything in tiny little pieces and concentrate your mass in atoms, so become finite statement, and the finite statement is like that. You have finite subset in the product of 3 sets, purely combinatoric, and then you consider projection to these binary projections, to the products, right? And so the statement is that cardinality behaves this way. So up there, this vertical bars refer to cardinalities, and dots meaning sets. 3 meaning it's kind of 6. There are 6 faces to the cube, and 4 faces for squares, so to speak. Why this notation? But they're sets, not measures. But for measures, we know there is this inequality for measures, as we observed before. And one implies another because you take the probability space where all atoms have equal weights. So it's a very simple case where entropy indeed equal by definition of entropy, or desirable definition of entropy, which we haven't defined, we only said but we want to. But this can be served as almost as a definition of entropy. So you use this equality, and also, but for projection, you use inequality. And if you just rewrite this, you immediately see inequality, and you see you lose kind of quite a bit of information because entropy is smaller. So you don't have equality unless projection actually have constant density. Yeah. Of course, projection of sets is a very bad operation, right? But push forward of measures is good for some reason. And then, however simple it is, read this question. So, Loomis-Whitney inequality is symmetric under permutation of coordinates. The question is, are there such inequality for other symmetries? And in particular, the usual isoperimetric inequality in this sharp form invariant at the isometries of the Euclidean space. But is there a similar inequality of this kind of degree of precision? And you can make conjectural inequalities, and that's unknown, though there are very closely related inequality for functions for densities, which I may mention is at some point. But so, however simple, you immediately kind of see that this is not, but by no means the end of the story. And this perspective of entropy, in my point of view, advantage, it's immediately bring forth questions which completely disappear when you look at the standard textbooks where you describe entropy. It seems there is nothing to do, yeah? But this shows you it's a very open field. Almost nothing is known, actually, yeah? When you look carefully from a certain perspective. And then this is an exercise which I suggest, which is related to that. It's again a very elementary statement, and just linear algebra. You have a four linear form, so in 4 variables over any field. And then you can divide it to variables in various ways, and you have binary forms. And each binary form characterized by its rank, not characterized, it has rank, and then, well, you have this inequality. And it's not clear why it's related to the Loomis-Whitney inequality. It's strong. It implies in a kind of trivial way, because very special forms you obtain this inequality. But the other way around is not completely obvious. And again, I don't know, and this is a question which begs itself, what in general relations one has. So given a multilinear form, you divide variables in pairs, and there are lots of ways to do this. Yeah, binomial coefficient. It's 2 to the n. I'm sorry, of different divisions. if n variables. And so there are 2 to the n numbers which are ranks. What are relations between these numbers? What are universal relations? So, and this is, of course, I don't know. And these are relations there. And this is, well, it has a connection with many things. And then I make little digression concerning genetics. Because it's a beautiful instance of where you see how probabilistic reasoning, little arithmetic, completely changed perspective in science. Yeah, if you look in application of mathematics and biology, this was probably the most significant. Yeah, it was really kind of understanding this basic property of evolution. Of course, of mathematics. Of course, it was known to Mendel. Yeah, it was kind of part for Mendel. Everything was obvious. But then again, the story was, my understanding is, when it came, Mendel didn't explain that. It was just apparent for him, and he didn't explain it. And he couldn't imagine that somebody wouldn't understand it. On the other hand, biologists of the time hardly understood multiplication table. It's just kind of obvious. They didn't understand numbers. And in particular, they were confounded by this identity here. That for them was impenetrable. I mean, it's obvious, yeah, yes. How they discussed this, and the issue, of course, not in this language. The question was to see it in kind of mathematical terms. And this, of course, was point for which Hardy and Warming done. They reformulated this phenomenon, and the phenomenon is that the next generation map is important. So I have the following map. Again, it's even Hardy and Warming didn't write in correct terms. When you consider matrices corresponding distribution of certain types of biological phenotypes, or rather genotypes secretly, seen via phenotype, and this is a very simple operation. On matrices, known as Segre map, then it has this property. And actually, if they are normalized, then it will be that, and well, an entropy enters in this way. So it's an entropically very interesting map. It's closely related to entropy. But what's remarkable about this map is square equals to itself. And this is amazing. It's a polynomial map on, if you normalize them by 1, and so it's polynomial map with square 1. And this is very rare when you compose polynomial map and you have 1, because degree adds up when you multiply, or just multiply. When you take supercomposition of 2 polynomial maps, typically, almost always, degree will be product of 2 degrees, right? But here it's cancelled off. And this cancellation, kind of strange, but I don't think, I made a joke to say this was a problem with biologists. Yeah. It's not, they understood that. Actually, Hardy himself, he wrote the formula, but he didn't realize it was a rather exceptional situation. And then, well, from this moment on, the kind of Mendel theory was accepted by biologists, which was the last obstacle. But it's from the very beginning the first obstacle. In my view, it's not understanding of, because as I said, Mendel has mathematical education, and the other biologists were infinitely far from that. For them, it was a completely mysterious thing. And now we come to the definition of entropy. And my point is that the point I want to make, that you can define entropy not as a number. On one hand, you need various property, but in fact, entropy is kind of a functor. And actually, recently, just 2 days ago, I received a message from Daniel Bennington when his collaborator developed even more sophisticated concept of entropy as some kind of cohomology, one-dimensional cohomology, and he think about higher cohomology. But because I haven't read this, I didn't understand what he says. Yeah, but apparently it is not surprising, and what I'm saying is probably the first word in a longer story, that this entropy, and I believe this applies to most basic physical concepts, are actually functorial entities. They are not about numbers, and numbers are just interpretation of 19th century. And now we're in 20, and for 100 years, mathematicians, especially modern physicists, were sticking to numbers, which is, well, there's nothing wrong with numbers, but that's a little thing of the story. And now I want to define this kind of first there are homogeneous objects, and then there are these reductions. And this is so we postulate homogeneous, meaning all atoms have the same weight, but again, it's a categorical notion. And then we introduce, and that's kind of essential, topology that you can compare different probability spaces even if you don't have them in one kind of universe, right? And that's a kind of typical problem which faced by physicists. We want description of something which makes sense even if you cannot directly compare two objects. Saying one equal to another, you have to really have physically transformation of the space moving one to another and then postulate this equality, so to speak. But just finding identical invariants is another story, and then we introduce these metrics using extra errors. So they're not reduction, they're just set maps between sets and even not everywhere defined, but these are convenient. So, but intuitively it's very simple. What is small perturbation of a measure space? And there are two small perturbations. One, you can take away some number of atoms of mass less than epsilon and add other atoms total mass necessarily epsilon. So the bulk of atoms don't change. And this epsilon modification, this gives you this additive distance. It's operation which atoms you choose and which don't encode it in this pi. And secondly, you may multiply all atoms by functions without changing atoms, but such that this multiplication not very big, but this is tricky how it normalizes. Because you see, you divide by the number of atoms. And that's tricky. Otherwise, and that's essential how you do that, because this is, and that's again typical when you try to apply something categorical to geometry, physics, whatever, you have to have conception of distance of something comparable. And then you add this together. They give you distance between two spaces, even if they're not both before your eyes. Yeah, they may be far away, and this can be communicated by telephone, so to speak. And then you minimize by all such correspondences. And this is kind of quite clear. They're close if you can make these two operations work. And then we have this asymptotic sequences of spaces. And this is again has kind of physical underpinning, is that you make measurement more and more precise measurements. So you have a big system, and P sub n means you measure its precision, growing precision, bigger and bigger machinery by which you measure. And then the equivalent, these results are equivalent if this distance goes to 0. And that is once you have in mind, today I explained how from that much of the kind of essential results of ergodic theory, of dynamic theory of Kolmogorov may be derived. And then you define this Bernoulli semigroup, what I call Bernoulli semigroup. It's just asymptotic classes of these sequences. So 2p and q are equivalent. If we take the high power and the right to infinity, they become equivalent. You see, that's very far. The original one will be not equivalent. But when you go there, they become equivalent. And and here the law of large numbers enters. And it says, this is just a reformulation of the law of large numbers. It's completely kind of simple. If you know the law of large numbers, it's obvious. And just you apply it formally to the function log on your probability space. And when you multiply space, log adds. And actually this, from my point of view, is much better than the law of large numbers, because there is no numbers though. Because in the law of large numbers, you have what's called random variable. Random variable, I just can't stand it. I don't know what random variable is, because it contains two quantities. One, probability space on which it lives, and then function which is there. But in reality, you don't know which probability space. You only observe something coming on random, and this is tremendous message. But in this form, there is no variable, no random variable. It's only spaces. There is no functions. That's the whole point, yeah? For the law of large numbers, you don't need any variable. You need only measure space itself. And everything depends on this. This is kind of the only, the right, in my view, the right formula. And of course, it has very simple interpretation. Yeah, you don't. Of course, what was kind of normalization was hidden in the definition of the metric. You know, the multiplicative metric was normalized in a certain way, and then it's here. And so this is what does it mean? Yeah. So it's two equivalent. And so every high power, eventually, if you observe something, the same event, the same machine, the same apparatus you observe it many, many times, the way it behaves, all probabilities become essentially equal, right? Equal up to a degree of precision needed for our purpose to define entropy. And then you define this entropy. So it's exactly how we can measure it now, right? Because how wide number of states. You see, it is coming from the number of states with asymptotic. So it's log of the number of states, but after you repeat experiment many, many times. And every experiment in physics must be repeated many times, otherwise I don't trust it, and then this is inevitable in the build-up in the whole philosophy of physics. Yeah. On the other hand, you can make the Boltzmann definition, kind of course, but not that Boltzmann saying that you don't use this the law of large numbers. You just say I had a class of equivalence, and then a posteriori with the law of large numbers, the two are equal. Yeah? But the first is categorical. You don't know a priori it's number, a posteriori it's a number, and in many cases, I guess it will be not a number. Yeah. If you know it's good reason for some cases, it should be a number. And so again, this equivalence, because the spaces go to the limit, so this group is just real numbers. It is nothing but numbers. And then there is this Boltzmann formula. Again, it's trivially derived. Again, now everything, once you take this law of large numbers, anything about entropy follows from the case of homogeneous spaces, when all atoms are equal. If all atoms are equal, it is true, therefore it's always true. You must be slightly careful how you go to the limits. But essentially, you don't have to think. This is still kind of tautologically, right, for space which all atoms are equal, right, where entropy is just log of the number of states, is that. Therefore, it's always true. However, this is taken often for definition, and this is, in my view, exceedingly, well, politely to say, incorrect, yeah, or naive, but I would say stronger, yeah, privately. It's extremely stupid, yeah, and. Because it hides kind of all that, and it causes difficulties in a way. But on the other hand, this is, I think it happens because mathematicians monkey kind of this ape this formula, removing k. But this is not only a formula; this is a very profound formula, and it has some significance, yeah. Exactly because it is constant, yeah. But then, this is a part, and then we just try to make it even more formal. If you really go categorical, you appeal to errors rather than to objects. And so you have a category, and you have errors, reductions, and then Grothendieck group. Now I say group, it was semigroup, actually. You can say group eventually, kind of, it's part of a semigroup, part of a group, which maybe I didn't have to do this, but here it's admissible. And actually, it's sometimes very pleasant to go to the group first. So I added these two relations. There are errors and there are two relations. And the first, typical for Grothendieck. The second, a little bit touchy, but that's essential for our purpose. And the moment you do that, you observe that, yeah, then as usual for objects, it's defined like that. You consider collapsing to one point, this error and this problem. This is standard kind of practice in categorical language. It's very kind of just make language flexible, nothing in there. Then you observe the distance which we defined makes sense for errors. So you have one space, goes to another space, so there must be comparison here, comparison there, and they must be consistent. So again, you know, categorical language tells you what it should be, and this doesn't cheat you. And so then it goes to the Grothendieck group, and then you just take this, divide space by these two relations, and then you introduce extra equivalence relation, which was Bernoulli, but this is much easier. You see, there is no powers involved, yeah? But you just say, so you have a group and you have a metric. So it's very now elementary situation, kind of very removed from what we have abstractly. You have a group and you have a metric on the group which is not invariant. And then you have two elements in the group are equivalent if you multiply them by a large number and they come close together. So the group kind of compresses thing at infinity. And So you take this distance, it must go to 0. Yeah, I didn't put it properly. In my page it was visible, but then, I see. And then there is a little point why it agrees with the previous discussion, because you can decompose Cartesian product, kind of this product agrees with composition of maps. Right? And therefore this group actually equal to the all group. And the law of large numbers, and here you have to look slightly more carefully at the law of large numbers and how things go, but it not only shows that powers of spaces can become eventually constant, but this can be done consistently. This approximation can be done consistently when there is a reduction of one space to another. It's kind of trivial, absolutely trivial. It requires no extra effort, but that's essential. And so the law of large numbers is functorial, right? So if you have several systems, you can do it consistently, though up to some limit. And in particular, what you have, so remarkably, you have this property, which is, look, why all this fuss, but the point of one, because it's this force due to the language, it happens, this equality, but I think it's just accidental, not true in general, but there are examples, even in measure theory, when you have infinite measure spaces, not finite but countably many atoms. Everything I said so far makes sense, but entropy now may be infinite if there are infinitely many atoms. However, entropy of errors may be finite, and that's typical in physics. You have infinite quantities, but their differences are finite. What makes sense of that, they must be implemented by something, by some mathematical structure. And entropy exactly does that. So it's not just a number, entropy. It's a way being assigned to it. And if you make the definition incorrectly, if you have two infinite spaces, you cannot say what difference is. And then, if you don't have categorical language, you always have problem. But in category theory, it's typical thing, how you relativize things. And this also all the time happens in physics. We live in this different world. Right? If the energy of the universe were just before us, you would evaporize immediately. Not just evaporize, we wouldn't be even vapor, we would be not even plasma, we would be as quarks. Right? But even with a relatively mild energy on the Earth, this already would destroy us instantaneously. Right? So, but we live on this edge when difference is relevant. And of course the same is true about our psychology. Right? We live by differences, and then I want to formalize a little bit this concept of joint. In categorical language, I gave one definition, which was set-theoretic, but in fact, when I speak about this joint, it means I have pair morphism. I have two objects go to one. I'm sorry, no. One object go to two. It's diverging fan. And there is an order on them, because one may factor through another. And the maximal or minimal one, is what I call this joint. It's not canonical in this category, but it's canonical after isomorphism. And what essential is the minimal fan, if you interpret them set theoretically, the map. So you see, in the measure category, all maps are onto. They're also injective. There is no injective map. However, the basic inequalities, and I mentioned today some basic properties, depends on some kind of injectivity. And the injectivity appears when you have two arrows from one space to two other spaces. And this resulting map to the product is injective, set theoretically, and also it's monomorphism in categorical language. So, because any category can be modified by considering particular kind of category of diagrams, and these are very simple diagrams. And this is what is written here. So, but then there is the following question: how much still the law of large numbers is functorial? As I said, for individual errors, it's functorial. But if you look for diagrams, it's not so clear, and probably it's not so. And this is a kind of combinatorial question. I thought a little bit, but I couldn't figure out. And so if you can approximate powers of all errors, if there are many objects and errors between them, so this diagram, this graph, and then you want when you go to the powers, replace everything by homogeneous, such that all kind of natural diagram commute. And for some diagrams it's true, but it's, in general I don't know if it is so. And that's a kind of basic thing in probability theory, of course, to know. I think the answer is no. But to finding extent by which it is true would be interesting. And what is essential, of course, you have to preserve property of fence in order to. But you have weaker properties which are sufficient, and so that's the point. And then there are the Shannon inequalities, which have already been written and they're indeed true. And now this thing is rigorously defined, this kind of joint, categorically. It was said theoretically, now it's categorical. They're the same, but again, when we want to generalize things, you go categorical. And the point is that now we can speak also about errors. And you had this complicated, remember this was Shannon inequality for overlapping measurements. And they were kind of more complicated formula, right? It was not direct sum, right? It was something else. But now it takes this much nicer form, yeah? You see, it's the same as they have for spaces. We had it for 2, now it's for many. But now if you write it for f and kind of spelled out, you come exactly to what you had before, yeah? And therefore you have this, we have this inequality. So again, you see there are kind of minus signs here. In f, there is no minus, because f themselves is a minus. And that's very, very typical. When you have this kind of error and relation, you always can secretly think to give you a difference between two spaces. And this, again, one of the basic tenets of categorical language. It's not a theory, again. Category, the way I use it, it's not really kind of a theory, but it's a language extremely flexible and simple, much simpler than set theory or analysis or whatever. Yeah? It's most primitive language available in mathematics, and really baby kind of level of language. But when you unfold it, it gives you a rather complicated thing, and we shall see it has some implications which are not quite obvious. But what I say it's much easier to remember kind of this formula, right? This formula, which is the same, rather than its corollary. What happens? Rather than its corollary, right there, yeah? Yeah, this is corollary which is rather heavy to remember. I cannot remember it actually. It's effort. It's a great effort to can remember it only, right? Who is plus, who is minus, etc. In fact, there are more corollaries of that. Yeah, this one of the corollaries which is exactly amounts to the Lebesgue theorem on high dimensions. Now it's n instead of k, yeah, I must admit. I always confuse indices. Yeah, I explain how things one are related to another. Okay, so this was more or less recollection of what was before, but what was before and now I want to pass to infinite spaces, infinite measure spaces. So the fact is that, again, categorically, whenever you have a category, there are standard operations how to enlarge this category and introduce new objects. And this is, and now, so given our category P, we can introduce, we have a bigger category which you consider the space over this category. And this, you use this kind of language. And this language, of course, is kind of, it's a little bit, may frighten you, but it's extremely simple thing. It means you have an object, new object with which you can operate as if it was in your category, up to some extent. Yeah? And here it means that, for example, if you have an ordinary measure space, of course, I hate what the usual definition, but on the other hand, it's nice. Then we consider measure preserving maps from abstract measure space, for example, interval to finite set. How you make this map, you divide it into pieces, cut it into pieces of weights equal to your atoms, and each piece goes to corresponding atom. And this is a set. And that basically this carries all information about the measure space. You don't have to know anything else. Just knowing this formal correspondence, because it agrees with errors between finite spaces, right? So everything you have to know about infinite spaces is encoded by finite spaces, and this, of course, how you do analysis. But analysis, you somehow you have no language to express it without introducing this ugly infinite space, which is really very unpleasant fact, but categorically it's very easy. And this new object you introduce, this functor, so it has value, right? So to each p, it assigns a set, right? And you can think about that you add this new object to a category, and then indeed you have a set of maps from X to any object of a category, and that's it. So you have this, because sometimes they're covariant, sometimes contravariant functor. When you say it, it's just extremely simple thing. So exactly, the point is that in measure theory, you don't need anything else. You don't need the set of the points, you don't need the points, whatever. All you need this relation. And as an exercise, you may, for example, see what happens to, say, Lebesgue integration theory. You just instantaneously come from that. You never come to Riemann integral. It's inconceivable, yeah? Riemann integral in this language. It's just all properties of integration come. And in a second, I say what happens to Lebesgue's density lemma. So there is one little point here, which I overlooked and somebody pointed out to me. Yeah. So when you do that, you have to take many objects in the same category. I mean, there is some logical point. With categories, you might be slightly careful with the language. I am not really good at that. Yeah. It's easy to make a kind of mistake. So you have to use language. It's a very convenient language, and everything goes exactly as you want, except you might be sometimes careful. And then there is a little point, and this is we had this operation in our category, and you want it to be there. So again, in measure theoretic sense, it says if you have two partitions of your measure space, you can intersect this partition, and you have again finite measure space. When you take finite partition of your measure space, it gives you finite measure space. You collapse all pieces to atoms. You have another partition, you intersect them, and you have thus you have these arrows between finite spaces. So this, and then this is an essential feature. So it's not just a covariant functor, but functor with this property, and that's all you need, right? So this basic operation still makes sense. And now, when you undo this object, this operation becomes non-ambiguous. So you have a category with additional operation. This finite spaces plus additional operation, and this encode this space. And again, of course, it's everything you do in measure theory, except you change your notation and just many things disappear from your notation. The point is, you have this, carry this weight and needed notation. You throw them away, and you already know what to do because of category theory. And this is what you call the measure space. And these measure spaces, so defined, are not exactly as usual measure spaces. They are somewhat more general. But they have all properties of usual measure spaces. They have no kind of, well, I don't want to say what the property they don't have, right? So, just again, everything is categorical, everything works just in an ideal way. All the operation you had now work. In particular, if you have a kind of transformation in these categories, all operation kind of become functorial and transform. And again, you don't have to think about that. It just allows you to be completely flexible with your notations and not introduce what you don't want to, what is needed. And here, this operation now becomes non-ambiguous. Yeah, this operation before it was somewhat ambiguous. It was manual operation, but when you add this x and everything governed by this x, it means kind of partition of given space, but you don't have to say it. Then all these operations become canonical. So you can use them systematically without saying any time there exists this or that, and become canonical. It's just language become more flexible. And there is this, what I said, this operation, minimal and whatever. And now come kind of some novelty. And so how we think about this physically again. And physically, it's extremely simple. So physically, you have this big system, this kind of, which kind of secretly behind it there is measure space. All you know about that you can have measurements. So you apply measurements, and it gives you a set of observations, something ticking. And this is my set. So physically, this is exactly what it is. Kind of physical system is a functor from my category of my machine by which I measure. So I have a machine for measurements, and they related one to another by arrows. So one machine may be used for observation, another machine, right? And this consistently, then we observe some unknown. This machine we know, it's our apparatus which we can make, we know something about them, but we observe a real object, and a big object in the world, and we have this consistent observation, and this means you have this covariant functor. And the question is how much you can see to see everything. And of course, as you know, when you speak about entropy of a physical system, it's a little bit illusion. So entropy depends. So what is the number of states, right? If we have some atoms under some temperature in quantum mechanics, they never reach certain states, and origin so rarely you can ignore them. So when temperature goes down, the number of states goes up, and this was known. It's very confusing for classical physics. One of the reasons how quantum mechanics came up. The entropy of a gas depends on the temperature, and kind of not how you would think it. So entropy is not even for this infinite system, even you assume you know what infinity means, it's not well defined. It's even more infinite. Yeah, it's infinite because it stretches in the direction of space, but it's also infinite because the other parameter is energy. And the deeper energy, the more energy, the more entropy. So there are many ways you have to normalize it. But however, but this problem kind of disappears if we have some definite class of measurements. So again, we don't speak about this abstract or real, about the reality of the system. We only try to organize what we observe. And then we can say this in a way that we have a sequence of observation and say it's full if within our means you cannot see more. So we describe in our machine for observation our finite measure spaces, and therefore only about them we see. And so we can say what do we mean to resolve it. It means if you add Q and nothing happens, right? And entropy gives you information, full information about the system. So everything you observe about the system is encoded by entropy. The number of states, we don't know what the states are. But if adding new machine, you see the same number of states, means you cannot see anything new. Of course, it may have become of different color, but then will be new states, right? So if you see the same, and from that point of view, entropy gives you full information about a physical world. There is nothing else but entropy, which is, of course, an overstatement, yeah, but the question of interpretation. And then an example. And this example will be essential to us. These are infinite products. And but maybe I'll come to this after the break because it's essential for what follows. Because today actually I'm planning to finish a little bit earlier. But that's, again, maybe I repeat, I want to emphasize this concept. So we make observation with some P's, meaning we just have this infinite system of observations, and then we couple them with other machines and see what we observe. And the point is the entropy doesn't change of these finite observations, right? Because it means you always for every Q there is another P, which when you add it you see as much as you see with Q in terms of the entropy. And this is how it's encoded in the language of entropy. And again, this is what's interesting in my view. That's what I say. Physically, just kind of obvious thing, you don't think about them, so naturally they are. And mathematically, when you, I don't know how to say it in a traditional language. Pages of formulas. Start writing some formulas. Completely immaterial. Yeah, it's just like you have to learn and exploit unrelated language. But maybe there is a better, again, I haven't read what Bennington wrote, maybe there is even better language, better meaning suggesting more structures behind it. Okay, so let's make a little break. So in probability theory, the fundamental operation is the fundamental operation taking products, which corresponds to considering independent variables, and even when they're dependent, you have something like products. And in this language, we can see infinite products defined by finite products of probability spaces are defined, and these infinite products must be something which is resolved by finite products. So you only consider projections to coordinate projections, and by these, everything is being defined. And there is one kind of minimal example, which essentially where the corresponding object will be topological counter set with a measure. So you have a finite measure space, you multiply infinitely many, you have both topology and the measure, and you can say, this is my measure space. In my measurable map, so to speak, it will be continuous measure preserving maps. It's again, from our point of view, it's a perfect measure space, and everything you will be proving will be true for that. And then there is a maximal one, and this is when you make this completion, in Kolmogorov theory, you make some kind of a completion of that. It's kind of it has some extra properties, and which are needed for most applications. Right? You do that because you want some universality. It's the same kind of like happens in the underway formalization of algebraic geometry when you have a universal field. However, when you look points over algebraic variety, you don't need this universal field, because if you consider all fields simultaneously, universality is built in. You don't need to make this universal object which is artificial anyway. And the same probability theory. This completion of Kolmogorov is needed, at least in ergodic theory. Sometimes you may use it, sometimes say if you look convergence almost everywhere, it's very convenient to have it. But in general, in many cases, you don't need it. And then there is this Lebesgue density lemma, which is entropically, some simple combinatorial statement. It's the only one which is needed to have full-fledged measure theory. And so I just don't want to repeat what it's written. It's just something about errors in this category. Something completely trivial. Whenever you state it in this way, it's a kind of exercise. And saying this is, which says that this, so it's essentially what it says, that these products are like usual interval. You just for your satisfaction, if you want to say that your theory applies to the interval with the usual Lebesgue measure, you have to say it. If you don't, you don't have to say it. It just, again, it's purely philosophical. You don't need it. And then in between, there is this, I bring in this formula when you have two spaces, one goes to another, then entropy of this arrow by this kind of formula. Again, this is one of the typical things which usually people speak about a relative entropy, which is, again, it is a kind of minor point because it's minor because it's not true in many more general contexts. Okay, so this is a kind of little discussion saying that there is a way to express basic property of measure spaces, which is people like very much in this kind of finitary language. Of course, when you go to the limit, but you don't need them for most of your work in measure theory, unless you start identifying abstract measure spaces, products with other measure spaces. But it's kind of trivial part of the activity, but this takes most, you see, like already heavy lemma, but it's completely trivial. You don't have to do it again. It's just only the question of purely comparing languages. And now we come to a more interesting issue. When you have infinite space, like a crystal, in my picture it is a crystal, and each atom may vary a state, and this atom interacts, and so it's infinitely many possibilities. So entropy must be, of course, infinite, but you have to normalize it properly. And so what we do is like that. So you measure it. We have this machinery, huge size n. We make measurements, finite but big. We take it entropy, divide by this size, normalize it, and go to the limit. And the question is how to do that. And there is no general recipe unless, and they all will be ambiguous, unless there is a symmetry. And the crystal is symmetric. And therefore, so what you know, if you take some piece of a crystal and go along, you assume, and you observe, nothing changes. You see all the same, right? So this is your axiom, and then, so what you say, you have your measure space. In measure space, you can say either is this functor or the whole category, right? It's just extension of our category. So it is something rather structural. So in this way, you measure space, instead of having sets and points, it has inside finite objects which are approximated, p, and there are errors between them, right? But there is no points, so to speak, right? You only sets are there. And it's very similar to the language of sigma algebra, but somewhat different, because it only everything concerns only finite sets. There is no infinite sets. Yeah, all sets are finite. And so imagine there are transformations which act on this p. So if you have a crystal and you have this machinery attached, when you transform it, it goes somewhere. So transformation can be applicable to this p. So we have a measure space, and there are transformations. The transformation applies to all p in this category, which lie under p. Again, of course, it's always like that. But again, the point is you don't have to speak about sets of partitions. And then we make this agreement. So you normalize by the size of the sets of transformations. So now my sets are not sets of some, we don't have concepts. We don't have a concept of the size of the apparatus. Only you know how many transformations we applied. And this non-ambiguous number. So you take one apparatus and move it in different positions, how many moves you made. And the point eventually we shall see is the material whom you move. That's the whole point of that. And this is how it works. And now, of course, how you move, this may change your results. But what I want to show, and that's kind of the essence of that, it's a material which p's I use, right? So if I have a sequence of measurements of my p's which resolve my system, in principle, I can see everything. And I have another system of measurement, another q's, which have the same property, the result will be the same. And this little kind of computation with Shannon inequality, right? And so this is a kind of the core of the proof of this existence of entropy. And this is again, excuse me. Hello? Oh, no, not now, I'm sorry. Oops. Yeah, because I expect some more important call, but not this one. And so this is what I want to show. Yeah, this is kind of the key when you use all this Shannon inequality. And this is finally, this certainly was in Shannon, but then it was by Kolmogorov set it into measure theoretic setup, and there was some kind of paper, and there were even mistakes in this paper corrected by Sinai. However, there is nothing there, as I explained, if you use this kind of formalism. And so we want to show if you replace P by Q, by some other system, nothing happens. If they resolve, again, P is something, the system of measurements will give you full picture of your P, a full picture of your X. And our definition of resolution that within finite system, there is no new observation you make, and that everything was defined only by what happens when you see by this finite kind of observational means. And so here is just. So this was definition of so how approximation works. And when we renormalize, now we take it bigger and bigger and make this thing, you arrive at this formula. So when you add Q, so you measure, you make observation without extra apparatus Q. And then you add this. And see that, of course, you see more when you add something. But the point is that in the limit, this effect will disappear. And so here is my notations. Right? And and what I use, of course, this relative Shannon and entropy formula. So it says that when you add this Q, nothing happens because of this inequality. And this is a little computation, yeah, which you have to make. And then this is exactly corresponds that kind of physicist kind of point of view that you have equivalent measurements protocol. And in one lab and another lab, you make some measurement, you get the same results. They're different measurements, but they're equivalent within these measurements. Yeah? So you can reduce one to another. Right? Anything you see in one, you can see in another. Then you can postulate that what you observe is the same object. So what you observe is a real world from this point of view is equivalence class of rules by how you observe it. And anything else is a kind of a philosophy. We don't. Are not accessible to us. But this amazingly fits in all with this mathematics. And so we come with this fact. And this is absolutely abstract and generally has nothing to do with group action or whatever. It's just that it's immaterial which P's and Q's you have unless they resolve your space. And now apply it to the simple example, and this is what Kolmogorov done. This kind of purely philosophical, again, modular the Shannon theorem. Shannon inequality was also proven conceptually, but this doesn't quite fit here, I must say. Yeah, it's not within this framework. So you still use numbers and inequalities, and I don't like it. So I don't know how to fully eliminate it. And then there was this theorem applied to these infinite product spaces. So this, and there was concentration on sequences. So I have sequences of infinite sequences, a distribution, their powers over one finite probability space. And then there is a theorem that if there is a measure preserving map between them, which is isomorphism, then entropies in P and Q are equal. So the simplest example which you may observe. So you may have one space with weights 1/2 and 1/2, which has entropy, well, some of these logs, like 2 log 2, and then you may have something maybe quite stupid what I'm saying, say 1 over 10s, 1 over 2 over 3, and whatever remains. Yeah, you can add. So this is a kind of measure space, and you only have to have that the entropies are equal. So here and here must be the same. Here is my PIs, here is QJs. I hate notation IJ, but when you write on the blackboard, they are numbered, yeah, 1, 2, 3, right? But before you write down this way, they're not. There is no numbers. Yeah? And so the equals QJ, sum of QJ log QJ. And then you have such a space. So it's atoms of different weights to the power z, and take another space. So you have these two spaces, and imagine there is a bijective correspondence, but measure bijective up to measure 0 as usual. Measure preserving commuting with action. Right? So the way I sketch it, they may have kind of equal. And then the point is, if it happens, entropy of this on this finite space equal to entropy of this finite space. And this was kind of a quite remarkable theorem. It was a big problem to decide when the Bernoulli shifts are the same. So here it's infinite spaces, but this compensated by the fact that there are equivariant maps. So secretly this entropy of a big space is this infinite entropy divided by infinite group and give you finite number, and you come back to what you start with. And this, of course, is a very general, very kind of fundamental kind of issue when you have kind of some physical system which you observe only kind of by not itself, but only when you repeat it infinitely many times. And this goes to infinity. You don't have individual observation. You only have a repeated observation, very large number of n. How much of this you can say? And here is that you can reconstruct entropy, nothing else, right? You cannot tell if they have equal entropies, but quite different, of course, then you cannot tell them apart. But the entropy is invariant, and the proof is just, after all being said, is kind of rather instantaneous. And the only kind of thing you use about integers is that, yeah. This bottom formula, where specificity of the situation enters. That if you divide n plus I divided by n, this ratio converges to 1. And so entropy p and it cancel off, of course, but this ratio converges to 1. For every fixed I. And that's all which is in there except for the generalities which I described. So, and then this was proven by Kolmogorov, a long time ago in '58. And as I said before, it's unclear to me. I haven't known enough kind of original papers in physics how much of this was understood by physicists. And in a way, they might have this idea in different language, of course. And also Shannon might have understood it. This I'm kind of, it's very, very unclear what was understood and was not. Because they were not, I don't think at that time there was any proper communication between different communities, like people close to Shannon on one hand and physicists like Van Hoff who were doing that. It's unclear to me, yeah. You can imagine that this was kind of obvious for physicists, in a way, in a way. That entropy, of course they understood that if you have a physical system like crystal, you measure entropy exactly. This is process of exhaustion, kind of, this Van Hoff theorem. And again, I guess it was known to physicists before Van Hoff, it was not written down, that entropy doesn't depend how you measure things if your measurement is sufficiently kind of faithful, if you don't miss something. And this kind of obvious, and it doesn't depend only on dynamics. But this point that depends only on dynamics maybe was not quite clear. I don't know. But anyway, it was done so, and then it was a little, in my view, nothing was happening for a very long time, because this argument applies to what is called to all amenable groups. So amenable groups, and this is just exactly the one, the class which is you can imagine in physics. So you have this transformation. I prefer to speak about actually like two-dimensional things rather one-dimensional. An essential feature of that, if you take big domains, properly chosen domains, then the boundary, the number of points in the boundary, significantly less than the number of points inside. So the boundary effect become negligibly small, so you can make measurement by using these transformations, and the error coming from the boundary will cancel out because the proportion of point is smaller. And these groups are called in general amenable, or generally such an array of points are amenable when you can exhaust them such that the number of elements of the boundary in the limit proportionally goes to 0 with respect to the number of points inside. And the typical example of a group which is not like that, and where all this, nothing of this applies, exactly, so what doesn't apply is this, yeah? This was kind of the narrow neck, the bottleneck of the proof. Again, everything else is just from general principles. Is free group with two generators. So, which is kind of maybe represented by a tree, right? It branches everywhere, and at every moment we have geometric progression, right? The sum of geometric progression is only twice bigger than the next term. So it grows pretty fast, and it was known, there were examples that this Kolmogorov theory breaks down completely. It breaks down completely. And then it quite amusing. Recently, a few years ago, it was discovered, it's still true for free group, so free group and two generators, or any number of generators. If you take again the same P and Q gamma, if you have two finite probability spaces in this power and they are kind of isomorphic, then entropy of P equals entropy of Q. However, what is not true, and this was true for a minimal group, if we have a minimal group and we have reduction meaning now equivariant map in this category. So it's again measure preserving map should be understood as in this abstract language, of course, but you can understand them also in the traditional way. So there is error which preserves measure, goes to measure, pushes forward to measure, and this gamma equivariant. If the group gamma is amenable, for example, abelian, then entropy goes down, which is not surprising. Yeah? You have smaller system, entropy goes down. It's not true for free group. And it was an example constructed prior to that quite a while ago by Benji Weiss with somebody, I keep forgetting the name. And then certainly it was clear that the whole theory as it is cannot work. And then it was done by Louis Boyne, however, that this is true. If there is isomorphism, then entropy is preserved. And that's interesting, is a kind of philosophy behind it. It's very close to the original one of Boltzmann, and even the way how it was presented by Kolmogorov, and then later on it was kind of refined by Sinai, but actually it was refined, and this essential point was lost, and partly kind of recovered by Bowen. And the point is that if you think about, if you read what Boltzmann says and how he thinks, he certainly operates in terms of non-standard analysis. For him, it was obvious there are infinitesimal and there are infinitely big time, infinitely small time, and then, of course, there was much of the statistical mechanics was formalized in set-theoretic language, not exactly how he meant it. And many things he said may look self-contradictory, because if you don't accept infinitesimals, of course, you cannot say what he was saying. And so what's interesting about this concept, about this theorem, that it uses, again, non-standard analysis. Again, analysis is just a word. When you use non-standard kind of logic, when you allow infinitesimals. So, and so the point is that the groups, the property of the free group and other groups where it is true, the groups are called, the group called suffix. So there is a class of groups which includes free groups and includes, in fact, all. It's not proven that not all groups are known to be suffix, but there is no group which is known not to be suffix. Of course, it's kind of absurd. Probably majority of groups are not with the property I'm going to describe, but there is no counterexample. All known groups which you can decide are suffix. And the idea of suffix is very simple and is as follows. So what is true when you have the group, which what I said is amenable? It means you can exhaust it by erase, so boundary will be very small compared to interior. Which means if I take any transformation in there, it's defined everywhere except on a very small proportion of elements. So the group approximately acts on a finite set. Another class of groups, another way to make act on a finite set is like a group like Z. Of course, say for Z, you can make it acting like that. It acts on this interval, ends go outside, but proportion of points going outside, negligible interval grows. So with any degree of precision, you can make it acts on a finite set. And there will be always proportion of situation when action has some problem, will go to 0 for any kind of property, any formula you write down, in the limit it disappears. And there are two different ways. One, like that, or you can make the group Z, the integers act on a finite group. On a finite set, you can make F act on Z divided by NZ. So you have this n gone, and you have rotation, and here action is perfect. There is no error. However, these are quite different kind of actions, and there are groups which act in one way but not in another way. Like free group admit this kind of action on finite sets with any degree of precision. And these are called residually finite groups. And then you can say, how well, let's make the definition. If there is action, just formalize what you have. You have approximate action on a finite set, and then we have bigger and bigger sets. We have bigger, better and better actions. And so you can say when you go n infinitely large, you have this finite set, but n is infinitely large number, and group act there. In more technical terms, you can say that Sophie groups are groups which act by symmetries by non-standard compact metric spaces. Right? So if you know this language, it's very easy to say. Naively like that. And then for these groups you have this theorem Boyle, and the proof is not that simple as Kolmogorov theorem. But really you have to go into computation in a much more profound way. And it depends kind of on all this kind of injectivity in there. So I don't want to dwell on this too much, because this is I want to arrive at something else, and so I want to finish today at that moment, because our next topic will be quantum entropy. So this is one direction, and the only the problem which I want to bring forth is, can you define entropy of these objects, like dynamical systems, in this category theoretic way? So I formulated somewhere. So our definition of entropy, I haven't defined entropy for dynamical system, which can be done by kind of approximation argument, and this is a kind of in a rather traditional way, except without mentioning measure theory. But the question is, what is the right category to define entropy for dynamical systems? And certainly, again, you know some properties you expect, and some of them, by the way, satisfied, and some not for Bowen entropy. You might be kind of somewhat careful. Again, there are kind of flaws, but it's the difficulty which I see, but maybe it's fake difficulty. Well, first, this kind of natural category you have spaces X acted with group gamma, and so you have a morphism which commute with these actions. But this category, you maybe have not enough errors in there to define proper entropy. And when we were working with finite measure space, we have additional errors as partial correspondences. And these are unclear what they are, should be there. You need, they serve kind of coordinate system, and then you cancel it away. And that's unclear if you can define this entropy, and if you define it, you have to compute it. And again, for this, in these examples of the Bowen with these Sophic entropies, it's unclear if entropy is unique, if it's a number or something much more elaborate. And this depends on this choosing particular non-standard models, and the things are not kind of coherent. So on one hand, there are these remarkable results, something invariant. On the other hand, understanding is missing, and there may be a fundamental reason for that. Yeah, so maybe you have to change concepts of the entropy more radically. But so this is a question, and then we start, and then next net. Oh, by the way, I have a misprint. Which I have to. So today I'll finish earlier, and we start with this subject next time.